The programmer, YouTuber, and Bezier curve propagandist Freya recently posted on Twitter about this Unicode character. In response, Laplace Fox said such a symbol might be useful with partial orders to say these objects are comparable. But what is a partial order? And what does it mean for two objects to be comparable? And how do partial orders get used? Before we talk about partial orders, perhaps we should introduce you to their more common partner, a total order. In a total order, every element is either greater than, smaller than, or equal to every other element, and the ordering is transitive in the way you expect. So if mice are less than cats, and cats are less than dragons, then mice are less than dragons. Lots of things in maths are total orders. The counting numbers, the whole numbers, and the rational numbers are all total orders. Even the horribly misnamed real numbers are a total order, but not the complex numbers. So, if you take any pair of totally ordered numbers, they will always be less than, equal to, or greater than each other. A partial order is like a total order, but as well as being less than, equal to, or greater than, we also have the option of incomparable. I think examples always make things better. The partial order that I encounter the most is dependency trees. When you are programming, you could put all of your program into a single file, but then you end up with a massive file that is impossible to deal with. Thankfully, we have a solution for this. We can split a program across separate files and have the main file import the secondary files. These secondary files can in turn have their own imports. So you get a sort of family tree of files. Now, the thing is, when you process or compile a program source into an executable file, you have to compile the dependencies before you compile the main file itself. If you treat less than as before, then if something has a dependency on each other, you can say something like JSON less than main. If you have a chain of dependencies, libxy is less than systemd is less than main, this chain of dependencies will follow the transitive laws just like you would expect. But if you try and compare JSON and systemd, there are no dependencies between them in either direction. So it doesn't matter which order you compile these libraries in. So we can say that these files are incomparable. What is even better is that because we now have a way to talk about partial orders mathematically, we can create a sorting algorithm. The sorting algorithm I'm going to use is adapted from NUFS, the art of computer programming. First, we create a source list with every item that you wish to sort, and we add along with a recording of the number of dependencies that this item has. Check the source list for items with a score of 0. Move these items from the source list onto the result list. 0 means this item has no dependencies. Since they have no dependencies between them, these can be done in any order, as long as they are at the top of the list. So it doesn't matter what order we add these to the result list, as long as they're put up to the top. We then take all the items in the source list and subtract 1 from any dependent on an item we just added to the source list. We can then repeat this cycle with the new items that have just dropped to 0. We will then repeat this until every item on the source list has been added to the results list. Well, that's the theoretical algorithm. Depending on your programming language, there are going to be slight modifications to work best with the facilities that the programming language gives. However, the biggest variation you're going to have to check is the state where you get a source list and there are no zeros, which means that there was a dependency loop of some sort. In that case, you should exit out with some sort of error. There are a couple of other variants on this system. You can modify this algorithm so it will work for scheduling paralleled jobs with dependencies. Make and similar build processing systems use this algorithm or a variant of it or an improved variant of it in their core. So that was one practical use of a partial order. Are there impractical uses of partial orders? Just partial orders that are fascinating for their pure aesthetic mathematical beauty? Yes, there are. Here is another example of a partial order. Divisibility in the counting numbers. You can say that a number is less than another in this ordering if that number is a factor of the other. So in this scheme, 2 is less than 4 because 4 has 2 as a factor. However, 2 is incomparable to 3 because they are not factors of each other. This creates a ordering structure that looks something like this, with 1 being at the bottom and all the primes being next after 1 and all the composite numbers being above their primes. And I just think this looks fascinating and beautiful. As long as you have a relationship that follows partial order laws, you have a partial order. If you find out a proof about partial orders, then you can apply it to everything that has this structure. Partial orders have a don't repeat yourself application to mathematics. Partial orders are also a foundation for the join semilattice and the meet semilattice, which in turn allows us to find the greatest lower bound, which is needed for calculus. I would love to continue up this particular tower of structures, so if there is enough interest, I'll make a video on semilattices and why we need them. You can show that you're interested by subscribing to my channel and sharing this video with people who you will think will enjoy it. Thank you very much, and I hope to see you later. Goodbye.